I guess it's time to get started, right? Today I'll be talking about our experience creating a new syntax parser that we use with Solr. So this is an hour-long presentation, and then I found out this morning that this is actually going to be a 35-minute presentation, and now probably a 30-minute presentation. So we better jump into it. Hi, my name is John Berryman. I work with Opensource Connections, and we do end-to-end search applications. You'll get to see a little flavor of that with the talk today. So today we're going to talk about the work that we did with the United States Patent Office, and part of that being building a new search syntax for them. We will explore what an examiner looks at. When he's thinking of search, it's a very, very different thing than your average user. Once in that section, we'll actually define the syntax that we're going to implement. The next section, we'll discuss whether or not Lucene has what it takes to do it, and it turns out well. Next, you have to have something to turn the strings into Lucene queries, and that's where Parboiled comes in. I found Parboiled to be a very interesting alternative to some of the more common compilers. And then we'll wrap it up by showing how to put it all back together into Solr, followed by questions. All right, so first things first, prototyping patents for patent search for the United States Patent and Trademark Office. In late 2011, we became part of the Patents End-to-End project. The goal of this project was to create the future of patent search. Now, little did we know that the future of patent search involved a 30-year-old search syntax that they simply could not get away from. So this is a rough kind of architectural overview about what the project was. Like I said, we do end-to-end search applications. So on one end of the spectrum, we had our patents in XML that we pushed through Tika and put into Solr. Classifications was another very large part of that. Classifications at the Patent Office are very complex. The classifications file by itself is about 100 megs of text, which is just hierarchies of how things work together. Patent images got pushed through bash pipes into S3, and is all served up by a JBoss API. The final product, the thing that was most visually I could explain what we did, was a JavaScript-driven web app. And you see here we have all the stuff that you'd expect from a normal search application. We have the search box. We have the results set with highlighting, which is interesting for this syntax. User history, et cetera, et cetera. The most important part, and probably the most interesting part for you guys, is the actual search itself. And so let's step out and get into that. How exactly does a patent examiner think about search? So to understand how a patent examiner thinks about search, it's good to think about how we usually think about search as, customers on Amazon or Zappos or something like that. Usually when you're going to Amazon or when you're going to Zappos, you're going with intent. You're going with something in mind that you want or that you need, and you're going to slice and dice the data set up until you find that thing. Once you find it, then you leave. I call this form of search needle and haystack search. Now, at the Patent Office, patent examiners are a little bit different. So rather than looking for something and then finding it and leaving, their goal is to prove, given a new application, their goal is to prove that nothing exists in that data set. Basically prove that in this haystack there is no needle. Now, obviously, you can't really prove that without going through every single document. So practically what this means is that an examiner understands the data set, knows how to slice and dice it, pulls apart the likely locations for a patent application to be related to, and then goes pretty much exhaustively through all the documents in that set. Historically, search at the Patent Office has been quite constrained over what we're used to. They don't have facets. They don't use synonyms, so they actually create banks of synonyms for themselves and send in large AND queries. They don't use stemming, and there is no idea of relevancy, so it's basically Boolean search. But it's powerful Boolean search. what this all implies is that they rely upon a very, very descriptive, rich search syntax. This search syntax is called BRS. No one remembers what BRS stands for, but that's what it's now called. And it is now our job to re-implement this search syntax in Solr. This is kind of the big point, right? So now, you're probably thinking, why not just use dismax? And sure, dismax is great. The syntax is really easy on the users. There's basically no syntax. You don't have to worry about what fields you're searching in. That becomes a matter of configuration. And when the results come back, even if you got 10,000 results, the user only has to look at the top 10 or 20 or so and doesn't have to filter through everything. That's great, except that our patent examiners just don't want it. Actually, dismax is the antithesis of what they want. They want exacting control over exactly how they slice and dice the data. They want to know where they are in the data set. And when you're actually looking through every single document in the small subset you found, relevancy is irrelevant, right? It just doesn't matter anymore. All right. So also, they're used to BRS, and there is kind of an inertia and political pressure just to keep the same thing. So for very practical reasons, also we are re-implementing BRS. So now, since we know that we're stuck with it, what is the BRS syntax? What is it like? You can do fielded queries. So I can look for something in the claims field, the description field, etc. It is Boolean search in the sense that you're used to. But importantly, they also add a very rich set of proximity operators. I can look for two matches in the same paragraph, in the same sentence. I can look for matches that are adjacent to one another, where order matters or order doesn't. So these four operators, same with adjacent and near, we've come to call those the SWAN operators. They're proximity-aware operators. Everything could be nested, so you can have matching spans within matching spans, etc. And just to give you an example, here's what the syntax looks like. In this case, we're looking for a widget right next to a gizmo in the same paragraph as a doodad. All this stuff has to be in the description field, and don't give me a document back unless it's also got a thingamabob. So there's kind of an idea of how the search works. So the question is Lucene up to the challenge? The gauntlet has been thrown. So right out of the box, Solr does come with some position support, but it's limited. Basically, it's phrase queries and phrase slop. You can't do any nesting, and the meaning of the slop is sometimes not as intuitive as you would think it is. But if you dig a little bit deeper into the Lucene code, Lucene actually does provide a very rich set of building blocks for position-aware search. These are the most important ones from our perspective. Span term query is basically a wrapper query that you wrap terms with, and that's kind of where you get started. That's the atom upon which everything is built. Span or and span not work as you'd probably expect by looking at the arguments there. No surprises. Span near is the only one that's really worth talking about for a little bit. Span near takes 3 arguments. The first argument is the set of all the subqueries that need to be near one another. The next argument is the slop, which indicates how near that these arguments must be to one another. It's an integer. And the final Boolean flag tells Lucene whether or not order of these terms, these matches, is actually important. There is a pain point here that we did run into. A span query is a type of Lucene query, but a Lucene query is not a type of span query. So sometimes it's hard to, you're doing a lot of casting and ugly stuff like that. In the future, I've heard that these two hierarchies of classes are going to be merged together, so I'm kind of looking forward to that. All right, so there's a couple different ways that you can implement the SWAN operators in Lucene, and we'll touch on the easiest one for now, the position gap strategy. So basically, prior to indexing your documents, you need to look through your data set and get an idea of, on average, or in a 90 percentile type case, how many tokens are usually included in a sentence. You need to have a number that is longer than the sentences. You also need to figure out, on average, maybe 90th percentile level, how many sentences are going to be in a paragraph. And so in both of these cases, just to be simple, we'll use an example of 50. Then, during analysis, whenever you get text into the analysis process, you need to add a position gap so that we have a little spacing between sentences and we have a lot of spacing between paragraphs. What that allows us to do is search near for two matches near one another. But if we say a number that is no larger than a sentence can be, then we know that we don't have to do any extra work. And similarly for a paragraph. So to give you a little better example, let's go ahead and jump into code and look how we implemented this. This is kind of a helper class that provides a bunch of static methods which I say, given these two arguments, same them together or with them together and give me some Lucene span query that is a valid implementation of that. So you can see here in the example of the same modifier, the left and right are the left and right span queries come in as the first argument to this new span query that we're making. We must make sure that they are within a certain distance from one another, max paragraph length, and order doesn't matter, so false. We've done a very similar thing with the with operator. Instead of paragraph, it's max sentence length. Adjacent operator, this is the only one where the order does matter. So we turn the last argument to true. And since we're talking about adjacency, the position is 1 now. And similarly for near, it's the same thing as adjacent, but order doesn't matter. Now, keep this class in mind, because later we're actually going to use this helper class to build our search out. All right, so let's take a look at how to turn the string arguments into a valid Lucene query. So if you want to parse your own syntax, there's a couple of things that usually come to people's minds, so-called compilers or parser generators. Antler and Java CC are two very popular ones. They're good. They're very good tools, but there are some complications with them. For one thing, you have to have an external search or an external syntax definition file. You also have an extra compilation process where you convert that file into bytecode or something that can translate your queries. And you run the risk of, with all these extra artifacts and processes going around, you run the risk of creating untouchable sacred relic code. It works. We're confused about what it's really doing, so no one touch it. So it's complicated. Parboiled is interesting, and it helps out in some of those pain points. Parboiled is a Parser Expression Grammar parser, which is kind of a mouthful. But basically, a peg is very similar to a context-free grammar, with the exception that a peg cannot be ambiguous. So in practice, this doesn't really get you into trouble if you're parsing a language like a search syntax. Obviously, you wouldn't be able to do natural language parsing with a peg. But Parboiled itself is extremely powerful. As a matter of fact, if you go to the website, one of the examples shows how Java itself can be parsed using Parboiled. So it's very rich, and it is of more recent updates, it's actually quite performant as well. The really cool thing about Parboiled is there is no auxiliary syntax file that you have to keep up with, and there is no extra compilation step that you have to keep up with. Really, the syntax that you write is code, and that code is the parser for whatever text comes in. So it's just one step. It's a Java class. As an example, let's look at a quick, simplified Parboiled implementation of a calculator. In this case, we're extending the base parser, and we're dealing with integers. So we're only adding up, subtracting integers. So an expression for our calculator is composed of a sequence of terms. Sequence of terms is composed of numbers. Numbers are composed of digits. I always like going in reverse order, so that's why I fast-forwarded. So let's think about it this way. When a new token comes in, is it a digit or not? Well, if it's 0 through 9, it's a digit. A number is composed of one or more digits. And by the way, if you see this match thing right here, it says whenever we make a match of one or more digits, we need to take that match, turn it into an integer, this is normal Java now, and push it back on top of a value stack that we're keeping track of. Now, in the rule higher than that, if we have already matched a number, then maybe we're trying to multiply or divide that number by another number. So we've made one match. If we find that we have an operator, a multiply or divide sign, followed by another thing that is a number, then we can pop both of those off, multiply them together, divide, whatever, and push it back on the stack again. Similar thing for addition and subtraction. And by the time you get to the end, you have your result. So using Parboiled, that talks about how to create your syntax. Using Parboiled is equally easy. You create a parser based on this class that you've just written. You take the arguments from your user and run it through the parser. And the result that comes out has basically an abstract syntax tree, that value stack. Now, in this case, it's really simple. It's just integers. So you can take the first value off that stack, and that is the result. All right, so now since we've got all the puzzle pieces, let's put it all together in Solr. So quick checklist. Are we ready? Do we have an understanding of BRS syntax? And yep, we've got the Boolean search plus proximity swan operators. So check. Do we have a way of implementing those queries in Lucene? And I showed you a class, it's pictured there again as a reminder, which will give us, every time we say give us these things samed together or adjacented together, it will give us a valid Lucene query from that. So check. Do we have something that can parse the syntax? I just introduced Parboiled, and it works pretty well, so check. And do we have the ability to package and configure this so that our users can actually interface with it? Yes, so that's where Solr comes in, and so check. All right, so now since we're ready, let's get parsing. In the next few minutes, I will take you through the different stages of the parsing, and we'll talk about how to get this incorporated into Solr as a plugin that your users can use. All right, so first things first is the Swan parser itself. In this case, we will be using Parboiled. Instead of taking numbers and evaluating equations, we'll take a user's input and turn it into Lucene objects. Now, you notice it's named the Wimpy Swan parser. The actual parser that we built for the patent office was considerably more complicated. There's a lot more nuance to the actual syntax than I've introduced. But this serves as this simplified version serves as a much better introduction to this type of work in Solr. All right, so again, I will scan through it really fast and then build it back up from the bottom. Queries are composed of ORed expressions. ORed expressions are composed of samed expressions, with expressions, adjacent or near expressions, and then at the bottom we get to terms, which are composed of characters. Okay, so now since we're at the base of this, then we have a little better idea of how things can work together. A character that you can use in a term is any number, lowercase or uppercase character, dash or underscore. Great. A term now is one or more of these characters together, so no spaces. And whenever we find one or more of these terms, we take that capture, take that match, create a Lucene term object, wrap it inside of a Lucene span term query, and push that on the stack. Next, if we have a term that matches, that has the near operator or adjacent operator after it and another term, then this is the piece of syntax that will since that that will take the matches that we pulled out of the terms, pop them off of the value stack, and then put them inside a Swan near query. Now remember, this is my helper class. So this is the class that I use to take these two arguments and turn them into a valid Lucene query. So we're still dealing with Lucene SpanQueries at every level of the stack. Keep going up. We have very similar behavior with the with expression, very similar behavior with the same expression. And then at the very top, we have an OR expression. In this case, we just use the normal Lucene class, the span OR query. And finally, once you hit the end of input, that's just kind of a special token, null, right? That signals Parboiled to say, all right, you're finished, halt, and return the results back to caller. All right, so that really is all there is to creating a Swan parser in Lucene. That should function. That should do just what you'd expect it to do. So in order to make it usable by your average users, we've got to stick it into Solr. And this is how you do that. There's actually two classes that are necessary to get this working together, but they're very simple. It's basically boilerplate code. First of all, you have to have something that extends a QParser. In this case, Wimpy's Swan QParser is that. You have a constructor that you can do whatever you want to with. We didn't actually use that for this example. And most importantly, you've also got a parse method. And this basically enacts code that we've seen earlier in the calculator example, but instead of doing calculator stuff, we are doing now position-aware queries. So first line here, you create a parser from that code, that class that we shared earlier. Once you're inside the Solr, this parse function, the query exists as this value right here, this dot query string. You pass that to the parser, and the result comes out as a span query. So you get the result tree, pull out the last value, and convert that to a span query. And finally, to fulfill the class, you just return that query, and Solr does all the other stuff of going to all the segment files and doing all the searching. All right, the other class is even more boilerplate than that previous one was. Basically, it's how Solr implements a singleton method. You don't need to recreate this fairly complex parser every time someone makes a call. So at setup time, Solr looks into all of its QParser plugins, and if it needs to, it initializes them. We didn't have any code there to demonstrate it. And also, when it's finally time to start searching, when it finally needs one of these parsers, it calls the create parser method, which returns an instance of the class above, and it's a singleton. So it doesn't have to do it over and over and over again. All right, so we are finished coding, actually. So at this point, you can use your favorite Java package manager, package it up, and push the code in the jar file into the Solr contrib file. The pathing with Solr is now straight. Solr will be able to find your code. And the rest is just downhill. Configuration, you need to make sure that you have this one line inside your Solr config XML. Not pictured here, because it would probably take another 30-minute talk, is how do you actually create the analyzer that once you have an input document that creates position gaps between sentences and big ones between paragraphs. That is actually very important. And finally, it's ready to use. All you have to do with the current configuration we have here is you have to declare your def type to be Swan. In this case, that was named right here. We named it Swan. And then instead of doing Q equals Lucene syntax, you do Q equals whatever you want to, Swan in this case. All right, so wrapping it all up, and potentially a little bit earlier than I thought. We've covered our work at the USPTO, something that I could go into a lot more detail if you'd like. We've examined how a patent examiner looks at search in a very different way from your normal e-commerce users. And we've defined the BRS syntax from that. We looked at kind of Lucene under the hood and found out that it offers a wide variety of position-aware queries that Solr does not expose immediately. We've talked about interesting alternatives to normal syntax parsing, in this case using Parboiled instead of the commonly used Java CC or Antler. And then finally we put it all together and implemented it within the context of Solr itself. So we're done a smidgen early. I look forward to any questions you might have.
I'd like to ask about your experience with this interesting notion of jumping positions ahead as a way of providing a no man's land supporting your sentence and paragraph searching. I'm wondering, it seems like both a clever idea and a hack, and I'm wondering what your experience was with it, whether you ran into problems. I mean, off the top of my head, if you ran into a sentence longer than you expected, you have to read
So that's actually a very interesting question, because I'm getting ready to tell you that's not how we actually did it for the thing. I didn't know I was going to go short, or I've talked about the other method, and the other method is actually the method we ended up going with, which also could be considered a hack as well, but it worked. The other method is to, when you analyze your sentences, instead of creating these position gaps, which could potentially be very large and just not work, you actually inject an extra token into the stream that says, I'm the beginning of a sentence, or I'm the beginning of a paragraph. And you just need to make sure that it's not a token that's going to occur naturally, maybe an unprintable token of some sort. And the queries that you have to create with these span queries, the side effect of that is they become more complicated. When you're looking for all matches within a sentence, you're looking for matches that don't also include this weird token, similar for paragraph. The benefit of this method, of the method that I demonstrated, is that as long as it worked, it would be much more performant, because the queries you're making are much more simplified. The benefit of the method that we chose is you don't have to worry about how long sentences are. You don't have to do all that thinking up front. So and it was performant as well, just not as performant as it could have been the other way. So actually, I just realized all the hassle up front. I'm selling books today, apparently. As you probably heard in the previous session, we are giving away books. And apparently I can choose whatever criteria I want to give away the book. So would you like a book? So this is the first person to ask a question. Seems like a good and fair criteria for me. This is Taming Text by Grant Ingersoll. I've heard it's a fantastic book. So the question was the bizarre absence in my example of the and query, because I had everything else, and I was wondering if anyone had actually noticed that. So in the 2 days before the conference, when I was feverishly reprogramming everything to make a simple example case, I came into the pain point of a span query is a query, but a query is not a span query, and they don't really cooperate. And so once you actually get into nesting span queries into a normal and query, that's fine, you can do that. But you can't go the other direction, and there's a lot of confusion in special casing, really, in the production code to get around that. You can get around all of it, but it's a lot easier to demonstrate without the and. Good observation. Okay, so the question was, in the initial slide we showed all the patents coming in, but there's also this little classifications thing that was going into Solr. That ended up being one of the most complicated pieces of this project. Now it doesn't really involve the search syntax. It's some of the stuff that it didn't show is like actually where you. So I take that back. There is a certain encoding of the classification, like D34 dot blah 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 dot, and so once you actually had to start parsing this is a classification as opposed to a normal term, that then parsing did become part of the picture there. But if you want to step out and ask the broader question just about using Solr with these classifications, that was a giant data set in of itself. And part of our document ingestion process was to find a patent, find the classification that what it was associated with, go to this other Solr index, pull out all the hierarchy above this classification, and it was actually a really challenging problem to get right. I could talk a lot about that, but probably not right now. All right, thanks guys.